We use it every single day, right? But how does the internet actually work? I mean, really work? Well, in this explainer, we're going to pull back the curtain and uncover the hidden journey your data takes every time you click. So let's dive in. Seriously, just think about that for a second. You click a link, and faster than you can blink, information from a server that could be thousands of miles away just appears on your screen. How in the world is that possible? It's not magic, I promise. It's actually a brilliant system of rules and protocols.
And to get our heads around it, we're going to follow a single tiny piece of your data, what's called a packet, on its incredible journey from your computer out into the big wide world and all the way to its final destination.
Okay, so before our little packet can go anywhere, it needs an address, just like a letter. Every single device connected to the internet, your phone, your laptop, your smart TV, it has one. It's called an IP address, and it's basically its unique ID on the network.
Let's imagine the entire internet is one giant global city. An IP address, like the IPv4 one you see here, is the one-of-a-kind street address for your device in that massive city. Without it, data would have no idea where to find you or where to go. It'd just be lost. And what's really cool is that this address is actually two parts in one. The first part, the network portion, that's like the name of your street. Everyone on your local home network, for example, shares this part. But the second part, the host portion, that's your specific house number. It's totally unique to your device on that street. This is how the internet organizes billions of devices into these manageable little neighborhoods.
So, with an address in hand, our packet is all set. But what if it doesn't need to travel across the globe? What if you just want to send a file to your printer or to another computer on the very same Wi-Fi network? How does it find a local neighbor?
This brings us to the next puzzle. See, we have the digital street address, the IP, but to actually hand over the data, we need the device's physical hardware address. It's kind of like knowing the address for a huge apartment building, but you still need to know which specific apartment number to buzz to deliver the pizza.
And the solution to this is this really clever little process called ARP, which stands for Address Resolution Protocol. You can think of it as the network's own private directory. Its one and only job is to find the physical MAC address that matches a known IP address on the local network.
So let's watch how this plays out. Here we have host A. It knows it wants to send our packet to the device with the IP address 10.0.0.5, but it has no clue what that device's physical MAC address is.
So what does it do? It does the simplest thing you can imagine. It shouts. It sends out this special broadcast message to every single device on its local network, basically asking, hey everyone, can whoever is using IPD 10.0.0.5 please tell me your physical address?
All the other devices on the network, they hear the shout, but they just ignore it because it's not for them. But the one computer that is using that IP address goes, oh, hey, that's me. And it sends a reply directly back to host A with its MAC address. And just like that, problem solved. The packet can now be delivered right to its local neighbor.
Okay, but let's be real. Most of the time, our data is headed somewhere far, far away. So what happens when the packet needs to leave our cozy little neighborhood and travel across the vast, open internet? Well, this is the first huge decision your computer has to make for every single packet it sends. It does a super quick calculation to figure out, is the destination on my local street, or do I need to hand this off to the local post office, the router, to get it started on a much longer journey? To make this call, your computer uses something called a subnet mask. You can think of it like a special lens or a filter. Your computer applies this filter to its own IP and to the destination's IP. In this first case, the results after the filter are identical. And that tells the computer, hey, this destination is on the same subnet as me. So it knows it can just talk directly using that ARP process we just saw. But now, look at this. The destination IP is just a little different. It's 192.168.2.2. The computer runs the exact same calculation, but this time, the results do not match. Ding, ding, ding! That's the signal. This packet is not for a local neighbor. It has to be sent to what's called the default gateway. And what is this default gateway? It's your router. You know, that little box with the blinking lights? It acts as the one and only exit door for all the data that needs to leave your local network. Any packet that isn't for a neighbor gets passed to the gateway, and from there it begins its long trip across the public internet. So now our packet is out in the wild. It's hopping from router to router, city to city, maybe even continent to continent on its way to the destination. This whole journey could involve dozens of stops. But
is there any way for us to actually see this path, to trace where it goes?
Well, to do that, we have to peek inside the packet's header. It's got a bunch of info, but for our story, the most important bit is this little counter called time to live, or TTL. Now, this isn't really about time at all. It's a hop counter. Its whole job is to make sure a lost packet doesn't just bounce around the internet forever.
The TTL works together with a special helper protocol called ICMP. Think of ICMP as the internet's own notification system. It's what sends back messages like, sorry, address not found, or, and this is the important part, hey, this packet expired because its TTL hit 0. And this is the absolute genius behind a tool called traceroute. It sends a packet out, but with a TTL of just 1. The very first router it hits lowers the TTL to 0, drops the packet, and sends back one of those ICMP error messages, which reveals its own address. Then, traceroute sends another packet, this time with a TTL of 2. It gets past the first router but dies at the second, which then sends back its address. By doing this over and over, slowly increasing the TTL, traceroute literally maps out every single hop of the packet's journey. So cool.
All right, our little packet has survived its long journey. It's finally arrived at the correct computer, maybe on the other side of the planet. But believe it or not, the job isn't quite done. Now it has to find the right application inside that computer. This is the final step, and it's handled by protocols like UDP, which use something called ports. So, if the IP address is the street address of the building, the port number is the specific apartment number. It tells the computer's operating system exactly which application this data is for. Is it for your web browser, your music app, an online game? The port number directs the traffic. So here's how it all comes together. The packet's IP address gets it to the right machine. Then the destination port number inside gets it to the right app. But here's the kicker. The packet also includes a source port, which tells the receiving application exactly where to send its reply. It's this complete round-trip addressing system that makes sure data flows perfectly between the right two programs, no matter where they are in the world. So, there you have it. From a simple shout on a local network to a continent-spanning journey mapped out by clever TTL tricks, all leading to a specific port on a specific computer. That is the incredible hidden life of a data packet. And all of this happens in less than a second, every single time you go online. It really makes you wonder, what other amazing digital journeys are hiding just beneath the surface of our screens?